There is a host of communication tasks where quantum resources offer an advantage with respect to classical ones. The future quantum internet, where any two nodes in the globe can exchange quantum information and at each node sits a full-fledged powerful quantum computer, will allow to implement all these tasks. But where do we stand now? What can we do today? Most experimental efforts have been directed towards the implementation of quantum key distribution. However, the situation is a little bit different depending on the physical medium chosen to transport quantum information. If we consider fiber optical communications, it is already possible to acquire devices for quantum key distribution from a number of commercial companies. With these devices, it is possible to distribute secure keys between parties that are separated by a distance of about 100 kilometers. With lab equipment, we can go a little farther, perhaps to up to 300 kilometers. However, for fundamental reasons that we will discuss later, it is not possible to go beyond this distance with a direct connection. It is possible, in principle, to go beyond this distance by co-locating intermediate devices that act as quantum repeaters. While this is possible in principle, this type of functionality has not yet demonstrated in experiment. There are a handful of other protocols, mostly cryptographic, that have already been implemented in the lab at short distances. Some of these have very similar hardware requirements as quantum key distribution. In consequence, we could expect that they can also be implemented over distances of a few hundred kilometers in the near future. Until we have quantum repeaters, there is a temporary solution called the trusted repeater. This is a solution that only works for the task of key distribution. The idea is very simple. Suppose that Alice and Bob want to distribute keys over 400 kilometers. Since they cannot bridge this distance with quantum key distribution devices, they call their friend Charlie for help. Charlie's lab is co-located just between Alice and Bob at 200 kilometers of distance from each. Then Alice distributes a key with Charlie using standard quantum key distribution, and Bob also distributes a key with Charlie. Finally, Charlie makes public the sum of the two keys. It turns out that provided that Charlie is trusted and does not leak any information, Alice and Bob obtain fully secret keys. This paradigm has been used since the early 2000s to distribute keys over long distances. Two of the most famous examples are in the slide. On your left, a metropolitan area network with trusted devices in Tokyo. On your right, an extremely long chain of trusted repeaters connecting the cities of Beijing and Shanghai. In the case of free space communications, the characteristics of fiber optical channels that do not allow to reach long distances do not apply to free space. In principle, it is possible to perform quantum communication tasks over long distances. The state of the art is shaped by a series of amazing experiments that the Pan group performed around 2017. They managed to distribute post-selected entanglement over a distance of 1200 kilometers. In another experiment, the group also managed to distribute secure keys between ground and satellite. And finally, with the help of the satellite as a trusted repeater, they distributed keys between cities in Austria and China. The need for a trusted repeater in this setup stems from the fact that the satellite does not see Austria and China at the same time. Hence, in the absence of a powerful quantum repeater that stores the quantum information sent from one of the parties and transmits it to the other party at a later time, it is necessary to rely on the paradigm of trusted repeaters. Let us go back to fiber optical channels and think from scratch why it is so difficult to reach long distances. Now I want to discuss what are some of the challenges for establishing long-distance entanglement, and a very idealized solution. Let us consider that two distant parties, Alice and Bob, are connected via a quantum channel. Since I am a theorist, we also imagine that Alice and Bob have noise-free quantum memories available to them, and even more, they can transfer qubits from their memories to the input of the channel and store incoming qubits into the memory without any error or decoherence. An initial strategy for establishing entanglement between them could be as follows. Alice prepares an entangled state locally between two qubits in her memory. Then, she takes one of the two qubits and encodes it into some degree of freedom of a photon and sends the photon to Bob via the fiber optical cable or channel. When Bob receives the photon, he stores it in his quantum memory. Now, Alice and Bob share entanglement. So, you might be wondering, what is the catch? The catch is that Bob might never receive anything. The probability that Bob receives the photon scales exponentially as a function of the cable or channel length. More precisely, let the d be the length of the cable, the probability is exactly 10 to the minus d over tau, where tau is a parameter that we call attenuation length that depends on the type of fiber optical cable. Let us go over a couple of examples to understand the implications of this exponential decay. Let us assume that the attenuation length is 50 kilometers. Then first, we can observe that every 50 kilometers, the probability of getting a photon from Alice to Bob gets divided by 10. It is 0.1 after 50 kilometers, it is 0.01 after 100 kilometers, etc. For instance, if we try to connect Delft and Madrid, which are at an approximate distance of 1500 kilometers, the probability of getting one photon to the other side would be 10 to the minus 30. Of course, we can partially compensate these photon losses by repeating the process many times. However, a quick calculation reveals that on average, Alice and Bob need a number of attempts equal to the inverse of the probability to transmit one photon. Hence, in the case of the Delft-Madrid link, Alice and Bob would need 10 to the 30 attempts on average. Let us transform this idea of repeating many times into a protocol for entanglement distribution that we call protocol A. In this protocol, Bob sends Alice a message indicating whether he received the photon or not. In the case it did not arrive, Alice resets her memory and tries again. Since these messages cannot travel faster than light, in the Delft-Madrid example, Alice and Bob would need to wait at least 3 times 10 to the 21 years on average to get their first entangled pair. Protocol A can be improved by multiplexing. That is, Alice does not need to wait for Bob's messages to try again. She can generate a new pair as soon as the first photon is sent to Bob. But even if Alice can prepare entangled pairs and store the corresponding qubits at high rates, long-distance communications are still out of reach. Let us call the rate at which Alice prepares entangled pairs the repetition rate. For instance, if the repetition rate is 1 GHz, Alice and Bob would still only generate entangled pairs at a rate of roughly 1 pair every 3 times 10 to the 14 years. Still not very impressive. Let us call this protocol protocol B. The solution to this problem is to place intermediate devices between Alice and Bob. We call them quantum repeaters. These devices basically exploit the teleportation trick to induce channels with larger attenuation lengths. Let us take a glance at how they work. Let us assume that we place a third party at half the distance between Alice and Bob. This party, we can call him Charlie, also lives in the idealized world I described above. That is, Charlie has a perfect quantum memory and can transfer qubits from his memory to the channel and vice versa without noise or losses. So, how do we benefit from the presence of Charlie? Consider the following protocol. Simultaneously, Alice and Charlie and Bob implement protocol B over an optical fiber cable of half the total distance. The rate at which these protocols produce entangled pairs over half the distance is 10 times d divided by 2 over tau times the repetition rate. The protocol in its link are asynchronous. So this implies, for instance, that when the first entangled pair is ready at one of the links, say Alice-Charlie, the other will have nothing. Since we have assumed perfect memories, this is not really a problem, since the link Alice-Charlie keeps the pairs stored and continues producing additional pairs. So once the other link, Charlie-Bob, produces the first pair, Charlie uses the entangled pair with Bob to teleport his half of the entangled pair with Alice. Now, Alice and Bob end with an entangled pair as desired. The rate at which this repeater protocol produces entangled pairs is equal to the rate at which the short links produce entangled pairs. That is 10 to the d over 2 over lambda times the repetition rate. So this rate is equivalent to the one that we would obtain if the attenuation distance had doubled or if the length of the link had halved. This idea can obviously be generalized to a larger number of intermediate stations. We can place repeaters between Alice and Charlie and between Charlie and Bob. In this idealized world, combining multiplexing, that is protocol B, with arbitrarily many quantum repeaters between Alice and Bob, then it is possible to completely eliminate the problem of losses in optical fiber. In summary, quantum repeaters can bridge long distances. In a sense, they allow to implement channels with larger attenuation distance. We have not discussed the effects of noise in this procedure. The preparation of entanglement corresponds with a sequence of quantum gates that are or might be noisy, and then the qubits are sent through a quantum channel that is also subject to noise. And finally, since the protocols we described are asynchronous, the parties need to wait for particular events to occur. In the meantime, the states in their memories decohere. So, similar to error correction, if one is willing to sacrifice the rate at which the task is performed, it is possible to take action against these noisy processes. In the case of entanglement, it can be distilled. The idea is that one takes several noisy entangled pairs and combines them into a smaller number of higher quality entangled pairs. The problem gets more complicated when there is more than one intermediate repeater. The base step is to distribute entanglement between adjacent nodes. However, there are several options to proceed from that base step. One can distill highly entangled states before proceeding, or one could proceed directly and distill after entanglement has been swapped. It is also possible to take different decisions for different nodes. At present, it is unclear what combinations work best. This is a very interesting open problem that needs to be tackled in order to distribute entanglement over long distances.